Hello, I hope all of you are doing fine. Now, in the last session, we have seen how we are going for balancing of the reciprocating masses, or we have seen how unbalance is getting introduced in a system due to the reciprocating masses. As well as we have understood that reciprocating mass, we are unable to go for complete balancing of the system. So, we are partially balancing the primary force due to this reciprocating mass, right. So, and we have as well seen that, so if this is our system, a slider crank mechanism, so which is turning at some angular velocity omega, and this is having some mass m, which is a reciprocating mass. Now, what we are doing is we are treating this mass to be placed at the crank pin, which is having a rotary effect, and then we are balancing it. Why I am saying it so is because in the analysis we have seen that we are balancing this unbalanced force due to reciprocating mass with the help of a rotating mass. That means we are treating this unbalance due to the reciprocating mass as a rotating unbalance, and that is why with the help of a rotating mass only we are balancing the system. Or in other words, I can say that when we are treating or when we are placing a mass at the crank pin, it is giving me the same unbalance, or it is giving same unbalance in the system as this reciprocating mass, and we are not completely balancing it. So, we are partially balancing it. So, we are considering a portion of this reciprocating mass, which is C times m reciprocating we have seen. So, this value of C, this fraction is somewhere from 2/5 to 4/5 of the reciprocating mass. So, this much mass only we are balancing, and we are treating this mass to be as if placed on the crank pin, which is rotating, and it is creating the same unbalance which is due to this reciprocating mass, and then we are placing a balancing mass diametrically opposite to the crank. So, this is this mass, so maybe at some radius, balancing radius, and this is that balancing mass we are finding out, right. So, that is how we are balancing this reciprocating mass in the system. Now, when it is partial, that means there is partial unbalance or residual unbalance in the system. And what is its magnitude? So, in the horizontal direction we have seen the unbalance in the horizontal direction, it is 1 minus C times m omega square r cos theta. And what will be the unbalance in the vertical direction? It will be unbalance in the vertical direction when I am placing this mass. Now, these two components, so this component, the sine component will be mb omega square rb sine theta. So, this is the unbalance in the system, and we can find out what is the total unbalance in the system. That is how we have seen. Now, this is this solution is we have found out only for the reciprocating mass. Now, there will be rotating mass also in the system. So, if you see this crank is a pure rotating mass. So, again what we do is we take a dynamically equivalent crank, you can say. This mass of the crank will be a distributed mass, right. So, what we do is we find out an equivalent mass which is again placed at the crank pin. So, this mass is the rotating mass, right, and mass of the crank. which is placed at the crank pin and which is giving the same effect, that of a crank of distributed mass. And now I am balancing this mass at the same location here. So here I'll name this as, say, MB1. Now MB1 is taking care of the unbalance due to reciprocating mass. So at the same radius, now for the rotating mass, if I place now another mass which is, say, MB2 mass, right, and this mass is taking care of the rotating unbalance of the system. So you can see that what is the total mass considered at the crank pin will be the complete or total rotating mass plus C times M of the reciprocating mass, right, which is at radius R. And this MB1 plus MB2, I can say, is the total balancing mass which we are placing at this location at radius RB. So now if I want to find out this balancing mass, so I can simply say that I can find out this balancing mass will be M rotating plus C times M reciprocating R. So I can find out what is the balancing mass required at RB, as well as I can determine. Now here you will see that the rotating mass is completely getting balanced. The unbalance which is remaining in the system is only due to the partial balancing of the reciprocating mass, right? Now there might be again one question in your mind is, what about the connecting rod? Now this connecting rod is also some distributed mass, right? So what we again do is we find out an equivalent, dynamically equivalent connecting rod. So the, say, the distributed mass of the connecting rod is something like this, right? So what we do is we take this, or we consider this entire mass as, say, this is M1 and this is M2, where this M is equal to the sum of these two masses, and we take these two concentrated mass and we place them at the two ends of the connecting rod, wherein, so if at given instant, if it is having some acceleration A and a moment M, so this equivalent mass is also having the same acceleration and same moment, and we place it here. So that means again here for pure rotating mass there is inclusion of this M1, and here at the reciprocating mass there is inclusion of mass M2. So this is how we distribute all the masses in the system and we place them. So as if this we are getting an equivalent, dynamically equivalent system, and then we analyze and balance the system, right? So when we say that pure rotating mass at the crank pin, so it is comprising of C times M, the rotating, and M1. So when and usually when it is mentioned that pure rotating mass, so that pure rotating mass is actually M plus M rotating mass plus M1, and entire reciprocating mass means this M reciprocating plus M2. So actually this is M reciprocating plus M2. So that is how we rarely when we say this is the reciprocating mass in the, if at all say in a given problem that the reciprocating mass is this much, that means as if it is including the distributed mass of the concentrated mass which has been separated out at the crank pin and at the slider, and then that is considered as whole reciprocating mass and whole rotating mass, right? So this is how we go for the balancing of entire system. So when we are finding out the solution by distributing all these masses, so we are getting a more accurate solution in a way. Now this is we are trying to understand this example with the help of only a single slider crank mechanism. Now if it is let us say a multi-cylinder engine, so that means the engines will be separated, right? So that means the reciprocating mass and rotating mass of one cylinder will be at one plane and of the other will be at the other plane. Now when these masses are distributed on a shaft, so it will be having a same crankshaft. So at same crankshaft, so it will be having, say this is cylinder 1 and this is cylinder 2, which is having reciprocating masses 1 and 2, right? And we have seen, so we are treating it this way, and then we can find out the balancing mass. Again we have seen while balancing a completely rotating system, we can select any plane, right, and we can find out the balancing mass and place them on those respective planes and balance the entire system. So the best way of understanding of balancing this system will be with the help of the locomotives, right? Now here what we are doing is, see, we know, or we are balancing the system, so we are finding out what is the required balancing mass in the system. But such systems are, again we are seeing that they are getting partially balanced. So there are when these residual unbalanced forces are there, dynamic forces are there in the system, so they do affect the system, right? So what can be their effect, that we will try to understand with the help of balancing or understanding the effects of partial balancing in the locomotives. So that will give us an idea which we can definitely then apply to various different systems for balancing, or we will be knowing what can be the effects of these unbalances in the system, and in a way maybe we can analyze or find out the limiting conditions of functioning of those systems. So let us try to understand this with the help of effects in the partial balancing of locomotives. So now let us try to understand the effects of partial balancing in locomotives. So as we have understood, we are unable to completely balance the system, so residual unbalances are there in the system and they do affect the system. So if you see what I have shown you the plan, so these two are the wheels of the locomotive and this is the shaft, and if you see the placement of, so if these two are the planes of rotations of the wheels, right? So cylinder 1 and cylinder 2, they are as if just at this location. So I'll say this is cylinder 1 and this is cylinder 2. So from top, if you see, that is how they are placed in the system. And we'll talk about another thing, the crank locations. The phase of the cranks are separated by 90 degrees of the cylinder 1 and cylinder 2. We'll see why it is done so, but this is how the system is. So this is the cylinder 1 and this is the cylinder 2. So they do have their own reciprocating and rotating masses, and there are unbalances remaining in the system. And these are, say, multiple masses rotating and reciprocating at multiple planes. So here these are two multiple planes, and what usually we do is we place the balancing masses at the planes of the wheels. At the planes of the wheels, by we mean that we are placing those balancing masses on the wheel, right? So if you see, if we see the side view for this, if you see, so this is the wheel, right? And So this is the tire, you can say, of the wheel. And you must have noticed in the locomotives, you must have noticed the balancing mass is placed on the wheels. So this kind of masses you must have seen, which are attached on the wheels, right? So if I take this point, so maybe this distance is the RB, and this is the balancing mass which we have put here. So this is the balancing mass, say MB, right? Now the effects, now I will name this as M1B, right? This total MB is actually due to reciprocating plus, which is taking care of reciprocating, and this is taking care of rotating. So this is the total MB, right? And the unbalance forces in the system will be only due to this component of the balancing mass. See, the rotating mass is completely getting balanced out, right? So that effect is completely cancelled out in the system. Whatever unbalance in the system is only due to this component of the reciprocating mass in the system, right? So that means now, so there are three effects predominantly we see in this systems. First, it is called as the hammer blow. Right? Second is the variation in tractive effort. So effort, we mean it is some force which is creating a traction kind of a thing. So it is a tractive force. And third is the swaying couple. So it is due to these two tractive force which are at phase. So this is creating a couple, unwanted couple in the system, which is swaying the entire system. So predominantly we see these three effects due to this the partial balancing of in a locomotive. So let us talk about this hammer blow. Now, as we are saying, so we are talking about hammer blow. Now we are saying that there are two unbalances remaining in the system. One is in the horizontal direction and the other in the vertical direction. So what is the unbalance in the vertical direction? Now this unbalance in the vertical direction is due to this, if you remember, this is how we have understood. This is the balancing mass 1, which is taking care of the reciprocating unbalance, right? Rotating unbalance is completely cancelled out. The effect is completely cancelled out in the system. So this MB1, instead of MB1, I'll write as MB reciprocating, right? Now this will be the force, and these are the two components we have seen. So this is the cos component, this is the sine component, right? So the vertical component will be MB reciprocating omega square r sine theta, and this is acting vertically, right? So now this value will be maximum, or the magnitude of this vertical force will be maximum when this sine theta is maximum, that is equal to 1, right? So when this is maximum, so I can say that this vertical unbalance due to this mass will be MB reciprocating omega square RB, right? So this is the maximum value, and this maximum value is called as the hammer blow. Right, so as if it is, why? Because this is varying continuously. When theta is varying, the magnitude of this force is continuously varying, and when it is maximum, as if when it is in the downward direction, as if it is hitting like hammer on the rails. So that is why this effect, due to partial balancing which is getting introduced in the system, is called as the hammer blow. Now this force hammer blow is at times acting downwards and at times it is acting upwards, right? So this force is, as the magnitude and as well as its direction is continuously changing. Fine. So how it is affecting the system? One effect is that it is putting a pressure on the rail when it is acting downwards. Now at one situation, if you see, the dead load also acting. So if it is having some mass m, so this mg is the load which is continuously, it is the dead load which is continuously acting on the rail, and this value of maximum, when it is both are in the downward direction, so they are together applying a pressure on the rail. And at times when this force is acting in the upward direction, so you can see, if this magnitude, if the omega or the speed is increased, if it is increasing at very high speeds, when the omega is increasing, then the magnitude of this force, vertical force, will be increasing, right? So that means the total, if I take the summation when both these forces are, so this is acting downwards and at times this is maximum value will be mb reciprocating omega square rb, right? So this will be, I can say, the minimum and maximum pressures on the rail. But if this value is increasing, if omega is increasing and it increases such that the magnitude of this component or this upward force is greater than the dead load, in that case the wheels will be lifted from the rails, right? So that means for a limiting condition, if I want to limit this omega, so if I say the limiting value, what will be the limiting value? Will be a situation where at least these two forces are cancelling out each other and just the contact is maintained with the rail. So I can find out this limiting omega or speed of the locomotive as, so if I take it this way, so it will be mg upon mb reciprocating into rb. So this will be the limiting speed, I can say. So if I know omega, then I can find out what can be the limiting speed. So that is how we can as well limit the condition of the locomotive, and as well we can determine what can be the maximum hammer blow in the system. So this is the first effect we understand, which is due to the partial balancing of the system. So let us now move on to the next unbalancing effect. So now let us talk about the variation in tractive effort. Now this variation in the of tractive effort is caused by the unbalanced part of the primary distributing force due to the reciprocating mass in the system, right? So before getting into the understanding, you will see that the cranks of a locomotive, when there are two cylinders, their phases are kept at 90 degrees. Now it will be maybe something like this if you see. So if this is the axis of the wheel, so this is one wheel, this is the other wheel, say, right? So you will see that one crank, if it is say in this position, the other crank is say, so you can see the crankshaft will be something like this. So if this is the connecting rod for the first cylinder and this is the connecting rod for the second cylinder. So if you see this condition, just try to, so this axis will be like this. So let me put it this way. So more or less something like this. So you can see the phase between the two cranks is kept 90 degrees. The reason is, say this is cylinder 1 and this is cylinder 2. You will see that maybe a situation can arise when the crank and the connecting rod, they are at 0 degrees. That means the transmission angle between the crank and connecting rod is 0, right? And when such situation is there where the transmission angle is 0, then the torque required will be very high to overcome that situation, right? So say for instance a locomotive stops at a place and incidentally the situation comes out to be this, then the torque required at this shaft will be too high. So if both are at the same phase, in that case both will be for both the cylinders the transmission angle will be 0, right? So in that case then the required torque to overcome the inertia will be too high. So that is why this phase is maintained, so that at least if one is for one cylinder, if the transmission angle is 0, then for the other it is a non-zero value. So it will be in a position to provide the required torque to overcome this situation of the other cylinder. So that is why this phase is maintained. And as I have said, the variation due to this tractive effort is due to the force, the unbalance force or the partial unbalance of the reciprocating mass. So if we see what will be the force, so now this force is the shaking force. It is the force which is acting along the line of the stroke. We have seen hammer blow. It is the force which is the jumping force which is acting perpendicular to the line of the stroke. So when there are two cylinders, so there will be two components of the forces which will be there in the system, or unbalances forces in the system. Say this is the first magnitude of unbalanced force in the system, which will be 1 minus c times m omega square r cos theta, right? And this will be 1 minus c times m omega square r cos. Now here the other one is at phase of 90 degrees with the first one. So if first one is this value, then definitely this will be theta plus 90, right? So I can say this F is total will be F1 plus F2, or I can say this is 1 minus c times m omega square r cos theta plus 1 minus c times m omega square r cos theta plus 90. So this will be the total force acting in the line of the stroke for these two, right? Some of these two forces which will be acting. So this will be an unbalanced force. So as if either at times it will be pulling the shaft or pushing the shaft with this amount of unbalanced force in the system. So and this value or this magnitude is continuously varying as the theta. It is when theta is continuously changing. So I can say that this F is 1 minus C times m omega square r. It will be cos theta plus cos 9 theta plus 90, right? Or I can say this is 1 minus C times m omega square r cos theta minus sin theta, right? So this will be this force which will be there in the system. Now this is continuously varying, right? So this value is continuously varying. So what can be its maximum value? So I can say this will be, this variation is maximum when df by d theta is 0, right? So when this is 0, so that means we want to determine or when we differentiate it with respect to theta. So now you can see, so if we differentiate, we will get this as 1 minus C m omega square r. So cos theta will be minus sin theta minus cos theta, which is equal to 0, or I can say sin theta is equal to minus cos theta, or tan theta is equal to minus 1. So this is what we are getting. So that means at, I can say that at theta tan minus 1, so it will be 135 degrees, and theta at theta 315 degrees. So at these two values of theta we will get this maximum variation, right? So for F max, so now when we have determined this value, so we can find out what can be this maximum variation so this F max, so this F is maximum at theta equal to 135 degree and theta at 315 degree. So we can find out when we put this value in that first equation, so we can get this maximum variation in tractive effort. So when we put this value, we will get this as 1 minus C m omega square r to plus minus root 2, or I can write it in other way, or this maximum variation in tractive effort, or maximum variation in tractive effort will be equal to plus minus under root 2 1 minus C times m omega square r Newton. So this will be, so by this will be the maximum variation in the tractive effort. So that is how we understand. So this will be the second effect, this will be the second effect which will be there in the system due to the partial balancing of the reciprocating masses. Again, this is only due to the reciprocating mass. That means this mass what we are considering here, m, it is the reciprocating, it is the reciprocating mass only. It is the component of the reciprocating mass, because the rotating mass is completely taken care of. The rotating balance is completed. They are cancelling out each other. This effect will be only due to whatever m we are considering here is the reciprocating mass, right? Only the reciprocating mass. So now let us talk about the third effect, which is called as the swaying couple. Again, which is due to the partial balancing effect. Now, say if this is the line of stroke, so this is the line of stroke of cylinder 1, and this is the line of stroke of cylinder 2. Now there are, due to this partial balancing, the unbalance in the line of the stroke is one we have seen, which is 1 minus c times m omega square r cos theta, and here this force, say this is F1, and the unbalanced force in the line of the stroke due to this cylinder 2 will be, now again this m what we are considering, these are all the reciprocating mass. This residual unbalances are always due to the reciprocating masses only. So here the count of rotating mass is not involved. So again, so 1 minus c times m reciprocating omega square r cos theta plus 90 or 90 plus theta, whatever you say. Now these two forces are acting along the line of the stroke, and say this is the axis of symmetry, and the distance between this two cylinder planes of motion of the cylinder, if I say take this as a, so this is a by 2, this is a by 2, right? Now what will happen is, when there is a difference between these two forces, right? So there is a difference between these two forces, whichever way they are acting. So now about the line of the axis, these forces will be giving or producing a couple. So about this line of axis, so this will be trying to move this way, and this will be trying to move this way. So what we can say what will be the total couple in the system. So if this total couple, if we see, this will be, this actually will be F1 into a by 2 minus F2 into a by 2, isn't it? So this F1 and F2 both will be acting in the opposite sense about the center axis. So that is how we will get the equation. Then it will be 1 minus c times m omega square r cos theta minus 1 minus c times m omega, again m means, again let me remind you every time, this is m reciprocating omega square r cos 90 plus theta, right? So that means we can say, so if I take this as common, so 1 minus c m reciprocating omega square r, it will be cos theta minus cos 90 plus theta. So it will come out to be then 1 minus c m reciprocating omega square r. So this will be cos theta, it will minus sin theta, so plus sin theta. That is what we will get, right? So this will be the total couple. So I again, last time I forget, so I name this as, say, right now equation 1, so that when we are putting the values for maximum condition, we are not confused in a sense, in a way. So for this variation or this couple to be maximum, then we can say that this dc by d theta, this must be equal to 0. So when we equate it to 0, we will get the maximum condition. So maximum condition for C or this swaying couple to be maximum. So we can say it will be then, so this is when we say, so this is supposed to be, then we can say cos theta will be sin theta minus sin theta plus cos theta. So this is supposed to be 0. So we can say that this sin theta is equal to cos theta, or directly I can say tan theta is equal to 1. So we are getting tan theta is equal to 1. Therefore I can say theta is for 1 tan theta to be 1, it will be 45 degrees and theta will be 225 degrees. So at these values of theta, we will get this C to be oh, I have missed a by 2. So I can, this will be a by 2. So this entire equation, this is couple. So we were making a blunder here. So this will be a by 2, right? So that means now the maximum value C max will come out to be, in that case, 1 minus C m reciprocating omega square r a by root 2 plus minus. So plus minus this value. So we get the equation this as the maximum swaying couple, or I can write it in other way, that this swaying couple maximum will be plus minus a by root 2 1 minus C times m reciprocating omega square r Newton meter. So this is the maximum swaying couple which will be there in the system. So that is how we see that due to partial balancing, these disturbances will be there in the system, and we need to find out these values so that we can limit the conditions and make the system run quite smoothly, or having minimum vibrations or disturbances in the system. So that's all in this session.